Hi everyone. In this video, we will discuss Taylor's theorem, prove it, and then look at several examples of Taylor's theorem in application. So to begin, let's look at a statement of Taylor's theorem. So Taylor's theorem uses higher order derivatives. So if the nth derivative of f is continuous on the closed interval ab, and if the n plus first derivative of f exists in the open interval ab, then for x in the closed interval ab, there is a point C in the interval between a and x, including a but not x, such that f of x is equal to this expression. Now, when we first look at this expression, it looks quite complicated, but if we actually just take and eliminate the series notation a bit here, we'll see that this is not quite so complicated. So if we take k is equal to 0, that gives me the 0th derivative of f, that's just f of a, divided by 0 factorial. By definition, 0 factorial is 1, times x minus a to the 0, but x minus a to the 0 will just be 1. So we get that our k is equal to 0 term is just f of a. Our second term when k is equal to 1 is the first derivative of f at a divided by 1 factorial, which is just 1, times x minus a to the first power. So the second term is just f prime of a times x minus a. And now if I continue here, so if I take my third term when k is equal to 2, I'll get the second derivative of f at a divided by 2 factorial, which is just 2 times x minus a squared, plus, and then if I continue up until the nth term, so the nth term would just be the nth derivative of f at a divided by n factorial times x minus a to the n. And then at the end, we get this term. Okay, so this is the n plus first derivative of f, not at a now, but at some point c, divided by n plus 1 factorial times x minus a to the n plus 1. Now, we can really think of this in two pieces. This piece we think of as being the Taylor polynomial of degree n. And this piece is often referred to as Lagrange's error term or the error term or the remainder term. I'll just say this is the error term. Okay, and so the idea is that my function f of x can be approximated by this Taylor polynomial plus some error term here, right? Now, in different areas of math, we use this differently. So for example, Taylor's theorem is very heavily used in numerical analysis, and there often you want to do analysis of this error term to understand how large or small the error in some approximation of a function may be. Okay. For our purposes, what we really just want to think about today is the fact that we can approximate f by this quantity here, right? By this Taylor polynomial of degree n. Okay, so our goal today, just to introduce a small piece of notation, we'll often abbreviate the Taylor polynomial of degree n as T sub n of x, and that'll be helpful here in a moment when we want to prove this, right? So again, the real idea here is that if your function f is continuous on the closed interval, differentiable on the open interval. So now notice we're saying the nth derivative is continuous. The n plus first derivative exists. Said another way, the nth derivative is continuous and on the closed interval and differentiable on the open interval. We just rephrase being differentiable. We rephrase the nth derivative being differentiable as saying the n plus first derivative exists. Okay. Notice also there's a sequence of implications. Since the nth derivative is continuous, that means the n plus first, or sorry, that means the n minus first derivative of f is differentiable, right? Similarly with the n minus second and n minus third and all the way down to the first derivative. The function itself, right, saying the nth derivative is continuous means that the function itself is n times continuously differentiable, right? So even though this looks like it's just a condition on sort of the last derivative here, that has implications, right, all the way back up the chain, so that we know that the function f, depending on how large n is, must be several times over continuously differentiable. Okay, so we want to see how we prove such a theorem. And given that I've sort of classified this in different parts, you won't be surprised to know that we're going to sort of consider the role that each part of this approximation plays. So let's look at a proof of Taylor's theorem. Okay, so the first thing we're going to do is we're going to fix a value x in the open interval AB. Okay, so again, if you go back to the statement of that theorem, it says, for a particular x, right, for x in the closed interval AB, there's some point C such that that equation holds. Okay, so let's fix an x here in the open interval AB. And the first thing we're going to do is we're going to choose a constant. I'm going to call it capital K. Okay, it's just some real number. So choose a real number K so that f of x minus the Taylor polynomial portion of that function at x minus k times x minus a to the n plus 1 is equal to 0. Now, anytime somebody says choose a real number such that this is possible, you should sort of say in your mind, well, how do I know that's going to be possible, right? So remember, x is fixed. So since x is fixed, my function is fixed, my Taylor polynomial evaluated at that point is fixed, okay? And so whatever this value is, this number is fixed, right? F of x minus t sub n of x is fixed. Similarly, x minus a to the n plus 1 is fixed, right? So really, all you're doing here is saying, well, I'm going to choose k to be the value that makes this equation hold where all of these things are fixed. This is like a linear equation. Okay, so since all these other things are fixed, you can definitely choose a k such that this holds. Now that k, of course, would depend on the x that you pick. You pick a different x, you'll need a different k. But for any fixed x, we can choose a specific value of k so that this holds. Okay. So now we're going to define a function phi. And sorry, let me call this, not to confuse it, I want to have a variable here, not that fixed value of x. So I'm going to define phi of t to be f of t minus t sub n of t minus k times t minus a to the n plus 1. Okay. Now, let's observe a couple of properties of phi. Okay. So the first is observe that phi is n plus 1 times differentiable. Okay, well, let's see. Let's just calculate out a few. Okay, so what is phi prime of t, right? Like, so how do I even know that, right? I'm sort of saying, well, look, this thing is true. How do I know that? Well, if I think about phi prime of t, the derivative of phi would just be the derivative of all of this stuff. Well, by assumption, f is n plus 1 times differentiable, so certainly it's once differentiable. T sub n is a polynomial of degree n. Polynomials of degree n are always infinitely differentiable, in fact. So this is certainly differentiable. And again, this is just a polynomial term. That's always differentiable. So I'll get a minus k times, bring the n plus 1 down, t minus a to the n plus 1. All right. So certainly this is differentiable because each of these pieces is differentiable. Now I can repeat that process, right? I could calculate phi double prime. It'll just be f double prime of t minus t sub n double prime of t minus k times, oops, and sorry, maybe some of you were yelling at me. This should have been t minus a to the n, right? The n plus 1 came down to the n plus 1 minus 1, which is n. So now in the second derivative, I have an n plus 1 that came down. Now I have an n that's come down, and now I have a t minus a to the n minus 1. Right? Now I can continue this process, right? Like I could go say n times. So the nth derivative of phi is the nth derivative of f minus the nth derivative of t sub n minus, let's see, what, by the time we've come down in derivatives, we'll actually be left with, so we had n plus 1, n minus 1, n minus 2, all the way down until the last thing that will have come down is a 2, okay? And so what we actually end up with here is n plus 1 factorial. And then we have a t minus a to the first power. Okay. Now, if we go one more derivative, something interesting happens. So if I go to the n plus first derivative, okay, I'm going to get the n plus first derivative of f at t. Okay. But now think about this. This was a polynomial of degree n. Okay. If you take a polynomial of degree n and differentiate it n times, what's going to happen? Well, all the powers are going to have come down. By the time you've differentiated it n times, this is actually just a constant. And then you differentiate that one more time, and the derivative of that constant is 0. So in the n plus first derivative, this term disappears. And here, again, this was originally this was a polynomial of degree n plus 1. So now when we differentiate it n plus 1 times, we're just going to be left with the constant, which is going to be k times n plus 1 factorial. Okay. Now, I'm going to, this proof, by the way, is in the book. So I'm going to not quite so much worry about writing out the exact words as I want to worry about sort of illustrating how we're going to use each of these pieces of information. Okay. So let's first note that because of the way I defined phi up here, from here, phi of A, what's phi of A going to be? Well, it's going to be f of A minus t sub n of A. Okay. Well, f of A, okay, this will be f of A, minus the Taylor polynomial, the only term that won't be 0, right? Remember, let's write it over here, right? This t sub n of x is the sum k equals 0 up to n of f sub n of a over n fact, or sorry, should be a k there. over k factorial times x minus a to the k. All right. So if I look at this, if I plug in a for x, your first instinct is to say, oh, well, then everything will be 0. But be careful, because when k is 0, right, we just get the constant term f of a. So because of this, t sub n of a is actually just equal to f of a. So up here, when we plug in a for t, we get f of a minus t sub n of a. But in fact, that's just f of a. And then when we plug a in here, of course, we just get 0. So we get that that's equal to 0. But also, remember this point x up here, right? We chose this x earlier, and we chose k so that this quantity, when you plugged in x, was 0. So phi of our particular x value that we chose here, right? Phi of that x value will also be 0. So what do I have here? I have a function phi that is 0 at a and at x. Therefore, I can apply Rolle's theorem. And by Rolle's theorem, there exists an x1 in the interval a up to x such that phi prime of x1 is equal to 0. Okay. Now, the idea is going to be, I've chosen an x1, now I'm going to choose an x2. The way I'm going to choose x2 is I'm going to come down here and now I'm going to look at phi prime. Okay. I'm going to again note phi prime of a is going to be 0. Okay. Now, why is phi prime of a 0? Well, what is phi prime of a? It's f prime of a minus t sub n prime of a, right? This term evaluated at a will again be 0. But what is t sub n prime of a? Well, if I take a derivative here, I'm going to get that t sub n prime of a is exactly f prime of a. Again, this is a Taylor polynomial. The whole idea of constructing a Taylor polynomial like this is so that the function and the Taylor polynomial have the same value and values of derivatives up to the nth degree. Okay, so this will again be 0. And I know that phi prime of x1 is 0 from the way I chose x1. And so now I have phi prime of a is equal to phi prime of x1, both of which are 0. And so again, by Rolle's theorem, there is an x2 in the interval a up to x1 such that phi double prime of x2 is equal to 0, right? So now the derivative of phi prime is equal to 0, or phi double prime is equal to 0. Okay. Now, we're going to keep doing this to obtain, choose a slide right here. Continue this process until eventually we will find an x sub n plus 1 in the interval a up to x sub n, such that the n plus first derivative of phi of x sub n plus 1 is 0, right? So notice what we're doing is at each step of this iterative process, we are finding a value x1 where the first derivative is equal to 0. We're finding a value x sub 2 where the second derivative is equal to 0. And we're going to continue this, we can continue this iteratively until we find a point x sub n plus 1 such that the n plus first derivative of phi at that point is 0. Okay. All right. So what does that give us then? So I want to now consider, okay, well, what does it actually tell me? I have now this point x sub n plus 1, so that so that the n plus first derivative of phi is 0 at x sub n plus 1. And so I want to think about, like, what does that give me? In order to do that, what I need to do is write out, what is the n plus first derivative of phi sub n. Now, of course, I've just erased that down at the bottom of the board here, but as you look at your notes, right, what is the n plus first derivative of phi at x sub n plus 1 going to look like? Okay, so this implies I've got 0, which is going to be equal to the n plus first derivative of phi evaluated at x sub n plus 1, but this was the n plus first derivative of f, and it'll be evaluated at x sub n plus 1, minus, remember that Taylor polynomial derivative piece disappeared, and then we're just left with k times n plus 1 factorial. Okay, so now if I look at sort of these two pieces now of the equation, I can solve this for k, right? And I must have k being equal to the n plus first derivative of f evaluated at this point x sub n plus 1 all over n plus 1 factorial. Okay, and so if I just say, well, that x sub n plus 1, that's my c. So setting c equal to x sub n plus 1 gives that f of x minus t sub n of x minus my k, which is now going to be f, or n plus first derivative of f evaluated at c, because I'm calling that c now, over n plus 1 factorial times x minus a to the n plus 1 is equal to 0. So just going back to that very first equation we wrote down, we said choose k so that this thing was equal to 0. Now all this work has been to figure out exactly what that k ought to be. Okay, and so now if I just rearrange this, right, what I've really got now is that f of x is equal to t sub n of x plus the n plus first derivative of f at c all over n plus 1 factorial times x minus a to the n plus 1, okay, which is precisely what we wanted from Taylor's theorem. Now, let's think through just a few implications as we look at this equation. And again, this really goes back to, sort of what does Taylor's theorem tell us? We would like to think that as this term gets small, right? So as x is close to a, that if x is close to a, then as n gets large, this should go to 0. Okay, and so what I'd hope is that while this goes to 0, this at least stays bounded, right? At least hopefully doesn't blow up and run off to infinity as n goes to infinity. So what I'd like to think is that, it's not unreasonable to hope that under some nice conditions, this term might go to 0 as n gets large. And therefore, what's happening is that the Taylor approximations are getting better and better and better as we take higher degree Taylor polynomial approximations. Now, as we're going to see, that is not always the case. And we are going to talk about this more in depth when we get to the sequences and series material and convergence of sequences of functions. We'll talk more about, precisely this idea of, what happens as n goes to infinity. But for the time being, just looking at this error term, we sort of think, okay, certainly if x is close to a, particular, right? So like this quantity is smaller than 1, right? If this quantity is smaller than 1, then as I take higher and higher powers of n, this term will go to 0. If that will go to 0, then I just really need that to stay bounded, right, to force this term to 0. If this starts blowing up, then I have to worry about some other things here, right? Maybe I need it to go to 0 at a particular rate or something to make sure this is actually going to 0. But again, that's in numerical analysis, people do spend a lot of time looking at the remainder or the error term to help analyze how quickly certain types of numerical approximation schemes converge. All right, so now let's spend the time we have remaining just looking at a couple of examples. We'll start with a fairly innocuous one first. So I want to look at the Taylor polynomials for natural log of 1 plus x. So let's start with the degree 1 Taylor polynomial. The degree 1 Taylor polynomial of a function is just the tangent line. Okay, so in order to come up with the degree 1 Taylor polynomial, I'm going to need at 0. So I'm going to do this centered at 0. I'm going to need the function value at 0, and then I'm going to need the derivative at 0. So I calculate the derivative of natural log of 1 plus x. So that's just 1 over 1 plus x. I evaluate its derivative at 0. At 0, that's just 1. And so now I can construct my Taylor polynomial of degree 1, right? So formally here, maybe I would say, right, this should be f of 0 plus f prime of 0 times x minus 0, right? But again, this value is 0. This value is 1. Okay, so I just get x back, right? So this is just the tangent line approximation again. Nothing too tricky going on here. And you can see here plotted, so the function itself is plotted in blue. Its Taylor polynomial of degree 1 is plotted in that red dashed line. It's a reasonable approximation, especially near A, right? At A, the whole idea of the Taylor polynomial is at 0, at the point that you're centering the Taylor polynomial. This Taylor polynomial, since it's degree 1, should match the function value and the first derivative. Okay. Now, let's take this up a degree. So what if I look at the Taylor polynomial of degree 2? Well, again, that's going to need to match the function value, the first derivative, and the second derivative at 0. Now, we already know the function value and the first derivative at 0. We just need the second derivative now. So we can calculate that. And then you get the degree 2 Taylor polynomial. Notice it's just the degree 1 Taylor polynomial plus you're now adding on this additional term, right? So this term sitting here, right, is really just what? It's f double prime of a over 2 factorial times x minus, and our a here is 0, so I should just say 0 there, times x minus 0 squared, right? So my f double prime of 0 is -1, so I get a -1/2 out here times x squared. That just comprises that additional term. And again, now I match the function value, the first derivative, and the second derivative all at 0. Sort of thinking another way, right? You're sort of matching the value, the slope, and the concavity at that point. Okay? And you can see here, you have in the dashed red here the Taylor polynomial of degree 2. It's a slightly better approximation for the blue function, right? The function natural log of 1 plus x. It's a slightly better approximation. Again, maybe it's a better approximation sort of for a slightly wider range of x values. Okay, if we sort of go back and compare it, you might say, okay, it's a little closer for a little longer, perhaps. Okay. But how can we make it better? Well, what if we take another term? All right, so we take another term. And I don't want to belabor this. You can check these calculations. We do this to get the degree 3 Taylor polynomial, and the approximation gets even better, right? So now I'm actually feeling even way better about this 3rd degree Taylor polynomial, right? Because, it's really sticking fairly close. Right, there's a little, you can see a little bit of error, say over here, but there's not a whole lot of error there, right? That's starting to be a pretty good approximation. Okay. All right, Again, I can take it up one more step, okay, the fourth degree. And as I start to do this, right, I can start to look at, so here's the degree for Taylor polynomial. I sort of start to maybe notice a pattern, right? So I've got x, and then I've got a minus 1/2 x squared, a plus 1/3 x to the third, a minus 1/4. So I noticed a couple things. One is that they're alternating signs, right? So I'm going to have like a minus 1 to some power here. The denominators are going 1, 2, 3, 4. So they're just increasing with each k. And then that k is the same as the power of x. So I can actually sort of write out this pattern here, which actually holds for all Taylor polynomials of every degree. Now, it turns out that if you take this Taylor approximation, it becomes a better and better approximation, but only up to a point. So this approximation, right, it's designed to be a local approximation. It's designed to approximate this function really, really well at a, right? In this case, at 0. It's just a happy fact that it may continue, like in this case, it seems to continue to be a good approximation for a little while, but we don't ever, well, without some additional analysis anyway, we don't know for how long it will be a good approximation, right? What happens right near 0, right? I'm only showing you out to 1 here, right? And in fact, here, this continues to be a good approximation out to 1, but not beyond 1. Okay, and again, we'll look more in depth at this later on. But these approximations, they're good up to some point, but not necessarily for every x value. Yeah. In particular, right, I could think about, well, what happens if I take n to be larger and larger and larger and larger? So, right, what happens if I just take this like infinite series here, right? It actually turns out, right, again, and I sort of mentioned this works as long as the absolute value of x is strictly less than 1, or if you go all the way up to x is equal to 1, that's okay. So essentially, it's a good approximation for x values. Said another way, we could say this works when x is between -1 and 1, not including -1, but including 1. So this infinite series, so if you think about taking an infinite number of ends, this gives us what we'll eventually define as a Taylor series, right? And for every value of x in this interval, it converges to the value natural log of 1 plus x. Outside this, however, this series actually will diverge, okay? So we have to be a little bit careful about saying that it's always a good approximation. So again, Taylor polynomials and Taylor series are designed to be local approximations, right? They're designed to approximate a function's value of its first derivative, second derivative, all the way up to the nth derivative, if we're talking about the nth degree Taylor polynomial. It's designed to match all those things at a particular point. It so happens, and again, we'll explore later, that might sort of continue for a bit, right? So you might be able to say that for some values close to that point, it also continues to be a good approximation. But as we'll see in the next example, that also might not be the case. So looking at the next and last example, let's consider this function. So let's consider psi of x, which I'm going to define to be e to the minus 1 over x squared if x is not equal to 0, and 0 if x is equal to 0. Okay. Now, a couple facts about this function. Okay. So if we were to look at this function, the first thing you might wonder, because it's sort of a piecewise defined function, is you might wonder if it's continuous, and it is continuous and differentiable at 0. Okay. Moreover than that, if you take its derivative is continuous and differentiable. And in fact, this continues infinitely. we would actually say this function is smooth. It has derivatives of as many orders as you want to take. So the 50th derivative at 0 exists. And it's also worth noting that the derivative exists for every other x value as well. So again, sort of, we can say even more that psi is smooth. So all, which means derivatives of all orders exist. Okay, so great. I feel pretty good about, like, I can use Taylor's theorem. Okay, I can write down what this means. Okay, let's see. So what, if I want to apply Taylor's theorem, then I need to start calculating the value of the function and its various orders of derivatives at 0. You can do this. You would use the limit definition of the derivative, have to play around with some things. What you will find, fortunately or unfortunately, depending on your point of view, is that the derivative is 0. Derivatives of every order are 0. Okay. And so what does that mean about the Taylor series, or the Taylor polynomial? Right, so remember that in general, right, this was defined k equals 0 up to n of, well, in this case, we're doing it for the function psi. So this would be psi kth derivative evaluated at 0 over k factorial times x minus 0 to the k. Okay, so this would be our Taylor polynomial approximation of psi at 0. But I just said all of these are 0. Okay. So the Taylor polynomials, there's only one. It's the 0 function. It's just the constant function 0. So what does this look like graphically? Right. So sort of what's happening here is that this function, which is plotted in yellow here, is incredibly flat at 0. And it's so flat that all of the derivatives of every order are 0 at 0. And that forces the Taylor polynomial to be 0. Now, in a way, what that means is that, like, it only matches the function at 0. Now, it matches all of the derivatives of the function here, but it's sort of a really bad approximation for this function anywhere else, right? Because the function, in fact, is only 0 at 0, right? And this doesn't change, like, as you take higher order Taylor polynomials, right? The Taylor polynomial of every order is 0, right? And so you just end up with this one not very good approximation. It's really only this sequence of polynomials is only going to converge to the correct value at 0. Okay. So again, well, in the other case, we saw that sort of each new degree added to a Taylor polynomial made it a better approximation. Here we see one that, in fact, doesn't change, right? And it's sort of not a very good approximation for any value of n. Okay. So again, we'll want to explore these further, and we will come back to these again in the sequences and series portion of the course. But I wanted to at least introduce some of those ideas today, having proved Taylor's theorem, to start our brains in thinking about these sorts of approximations. Now, a final question we might ask is why approximate things by polynomials? The short answer is that polynomials are easy to work with for a number of reasons, right? So the first reason that polynomials are easy to work with is that they're very easy to calculate things with, right? If you think about it, if I want to evaluate a polynomial, that's what? I need to be able to exponentiate some number, which is really just repeated multiplication, multiply it by a coefficient, that's just another multiplication, and then add and subtract terms, and that's just an addition or subtraction. Computers are much more efficient at evaluating polynomials than they are at, say, evaluating just some exponential, right? How would you tell a computer, which at sort of a base level knows how to add and multiply, how would you tell it to evaluate an exponential? Well, you might approximate that exponential by a Taylor polynomial. And again, you use that remainder term to know how many terms do I need to make sure my error is relatively small. These are sort of classical questions in numerical analysis. But the other reason that this is important is that we know lots of theoretical results for polynomials. Polynomials are nice and continuous, differentiable. We can do lots of things with polynomials that are hard to do with a generic function. So what we may want to do sometimes is use a approximate function, right, to prove something, and then show that because it holds for that approximate, that we can also apply the same result to the original function because they're not very far apart, right, in some appropriate sense of distance between functions. Again, that's where that remainder term comes in helpful. So Taylor polynomials give us a way of sometimes substituting what could be an ugly function with a polynomial, which are much easier to work with.